Okay, here's another example of trying to find a contour diagram for a function. This one goes outside of our zoo just a little tiny bit. We'll try to fit it back into the zoo at the very end. But meanwhile, I just want to find some z values, see if I can't decide what the contours look like, draw some things, and then see if we can't make it better. Again, the very first step in making a contour diagram is pick some appropriate z levels. Z can't ever be negative here. The only time a square root can be negative is if there's a minus sign out front. So I'm going to do what I did before, and I'm just going to pick some, let's just go to 3 and see what we can do. If someone said graph this for each of these, unless you actually recognize it, what I want to do is to solve for y. So let's square both sides. Those of you who haven't squared things like the braces, your TI calculators will accept input like this, which is great. Solving for y, let's see here, I want to get y on one side. I'll throw the y's over there, the numbers over there. So I'm going to get something like y squared equals, let's see here, x squared minus, and in parentheses, 0, 1, 2, 3, squared like that. I'm going to take the square root of both sides. Remembering I now have to use plus or minus. Y can be negative here, so I'm going to get plus or minus the square root of x squared minus 0, 1, 2, 3. At least I'll get 4 contours that way. Now, we have to dig way back into your past. What does this look like? This is actually, each one of them, except the first one, is a hyperbola. We'll talk about what part of the hyperbola we have to draw. But meanwhile, I'm going to take this thing here, I'm going to put it up at the top, and then just draw the contours. So let's just erase this here so we can have the whole screen for just drawing the contours. I'm going to get y equals plus or minus, and then I get x squared minus, and then braces, 1, 2, 3 braces, squared like that. And what am I supposed to do? I'm supposed to plug each of these values in at a time and just see what's going on. And I'll try to draw this as big as I can. Reasonably accurate. We'll try to draw some conclusions later. Remember, this is x and this is y. We're taking slices and we're taking the pictures of the slices and just projecting them down into the xy plane. Now, when x is 0, all I get is y equals plus or minus the square root of x squared. Well, that's y equals plus or minus x. So what I'm going to get, this is one of my contours. This is when z equals 0. Actually, there's no reason at all, well there is, but to make that dotted. Here's another contour. This is also z equals 0. So this says basically, if I'm looking down at my solid, whatever it is, if I happen to start walking in the origin, I walk that, I'll always stay at height 0. Same that direction, same that direction, same that direction. Now, when you plug in the value z equals 1, I'm going to get y equals plus or minus the square root of x squared minus 1. That actually hits the point 1, 0, and this one over here will hit negative 1, 0. And what is this? I said these were hyperbolas, and they all actually have the same asymptote. So they come like this, and then this one comes like this. It gets very close over there. This one goes like this, and hits like this, and then just go like this, and hits over there like that. When I plug in the value 2, the inside becomes the square root of x squared minus 4. This actually hits at 2. So we at least get nice numbers here that we're hitting. And each of these, again, is a hyperbola with the same asymptote. So this is getting, by the way, very jammed up right here. These are the contours. That should mean over there it's getting very, very steep. Again, here we're having very crammed up here. Hits very evenly spaced here. It comes like this. When I plug in the z value 3, the inside becomes x squared minus 9. And so that's going to hit at 3. That's going to hit at minus 3. And again, this is a hyperbola with the same exact asymptote. So real down here, it's getting really crammed up. Like that. And then like that. Really crammed up here. Really crammed. It's going to get like this. And then nice and evenly spaced. And then really crammed up here. All right, so it looks like it's going to be very steep over here and here. Very steep over here and here. You can see what it looks like Actually, I think if we were to go to Desmos, we'd actually see this exact same thing, except better drawn. But I like having the z-values. For example, having the z-value 0 here means, and I think we talked about this in just a second ago, if we walk along this, we always stay at height 0. If we stay at this, where it always stays at height 0. Now what happens if I'm on this surface and I walk along the x-axis from here to here? Well, all the z-values are evenly spaced and they go down to 0. And then all those z-values are evenly spaced and they go up from there. This says if I chop whatever the surface is like this, it looks like absolute value. So this is a kind of a strange thing. If I were to walk from south to north, I would hit nothing. There's no graph, no graph, no graph, no graph, no graph. All of a sudden I hit z equals 0. I hit z equals 1. It goes up a little bit, and then hits z equals 1 and hits z equals 0, and I have nothing again. The only thing that we actually have in our background that does that is a piece of a circle, right? So it looks to me like if I take chops of whatever this is, this way, I get circles that sit up like this. If I chop this way, I'm thinking I get hyperbolas. If I chop right at the x-axis, I get absolute value. That's hard to figure out exactly what's going on, so what I want to do, although this is not taking contour diagram anymore, is to look at our original function and see if we can't decipher what was actually going on. Remember, our original function looked like this. And I'm just trying to get as much learning out of this example as I possibly can get. I'm going to square both sides. Now, I did just add negative z values to this, and we'll worry about that in a second. So I'm going to get z squared equals x squared minus y squared. I'm going to solve for x squared. That's x squared equals z squared plus y squared. So that x equals plus or minus the square root of z squared plus z squared plus y squared, like that. Now, why do I bring that up? Because this is a sideways cone. Our regular cone looks like this. Yes, and opens up in the positive z direction. This is a double cone, right, that opens up in the positive x direction and a positive y direction. So this actually, from side to side, is just, I'm thinking, the top half of something that looks like that. And then I think all the chops start making sense. If I chop like this, I get circles. Yes, if I chop along this and this, I just hit the line. If I chop like this, we get hyperbolas. So this is just the top half of a sideways double cone. And if you remember your Greek mathematics at all, oh boy, is that important. Anyways, that's the end of this example.